Hello everyone and welcome to the new discussion. Basically it is a series of discussion on groundwater exploration, and in this one we are having part 7. Some of the aspects we have discussed in the earlier discussions on groundwater exploration, especially in the previous one about the geological and hydrological explorations or understanding about the area, and we will further look in this direction or have a more discussion on this. So, as you know that first and foremost task when we go for quantitative evolution of groundwater resources based on surfacial informations, remote sensing based information, geomorphological or geological informations, we can make some assessments about the quantity or availability of groundwater resource. But for us it is more important to have better information about a complete quantitative evolution of the resources or estimation of the resources, and basin wise properly identify basin boundaries. Why? Because we know that these watersheds or basin boundaries are basically topographic boundaries. But same time we have also discussed when we were discussing watershed and springshed, that they are two different entities or two different features which are there. So, generally we do not have much information about the subsurface geology or subsurface arrangement of rocks. So, we go for basin boundaries, which is a topographic boundary. Why? Because the water or rainfall is occurring, and whatever if it is occurring on in a basin, then it is assumed that whatever the water is precipitating will flow through an outlet, and that is why basin boundaries are important to identify, but sometimes you may not get. So, in this figure what we see, different types of conditions are there, different types of scenarios related with rocks and topography. So, here what in the first one A, what we see that if precipitation occurs and if we are having this kind of undulating topography, which is a very common phenomena in case of a granitic rock, and that is not as flat as the Indo-Gangetic plain and may not be as rugged as Himalayan terrain. So, you are having a very smooth kind of topography, and we say undulating topography, and generally the water table will follow also this undulation of the topography. So, in the bottom you are having the granite, and because of these in this example because of these two humps, the basin boundary would be here. So, whatever the water falls here will come here, whatever the water falls then it will go on the other side. So, similarly in this situation is there, and as I mentioned, water table will follow more or less the topography, undulating topography. And this is a completely granitic terrain, top part may be weathered, fractured. Now, we come to the another scenario, it is B in figure B. Again these two two mounds are there, and again undulating topography, and this is a sedimentary sequence that on the top you are having sandstone. So, in very brief it is written in abbreviated form, it is written SST, and in the bottom you are having the shale. Sandstone is good, having high porosity and permeability. Shales are fine grained rocks, will have high porosity, but may not have good permeability unless it is fractured or the thing. So, what would happen then, like here the watershed boundary or basin boundary was at the apex of these mounds, but here see that the watershed boundary is now topographically the watershed boundary would be here, but you see these arrows are suggesting that water from other side of this watershed boundary means from other basin can come in here also. So, in sedimentary sequence and this kind of arrangement of sedimentary and shale layers, which can the shale layer will serve as an impervious layer. So, then water of other basins can also run. So, it is a interbasinal movement of groundwater, that is also very likely in natural conditions. And third scenario is here, where you are having metamorphic rocks, you are having schist, and you are having a fault which is also shown here. So, here again these mounds, if precipitation occurs, they need not to serve as a watershed boundary. As you can see that along the fault the movement is happening, which is interbasinal movement. And in the last or the D, what you see here that this becomes a leaky aquifer conditions, where the piezometric surface of water table is here, and you are having some fractured rocks there, and then some sedimentary rocks are there, which becomes your leaky aquifer. And so again these mounds that geomorphology or topography will not control the groundwater movement. So from top you may delineate based on the contour lines a watershed, but really in subsurface conditions it may not be there. But still, because many times we do not have such detailed information about subsurface condition, and therefore we always most of the time rely about the basin boundaries. So sometimes when we do not get the expected results, then one should always try to understand what is beneath the earth, what is on the top layers, how they are behaving, what is the attitude, how they are fractured and weathered. And if we can get some information about subsurface conditions, then we can understand the subsurface flow and water divides, groundwater divide. So what I am trying to say that groundwater divides and water divide on surface need not to be the same all the time. All will depend, the groundwater divides and topographic divides, all will depend on your rocks and their arrangements. So topographic divide will depend on on the surface elevations, changes in elevations, whereas groundwater divides will depend mostly because of arrangement of different rocks and layers. So lower aquifer contributing in all these to recharge the phreatic aquifer in one part of the drainage basin, while the discharging to a lower aquifer in another parts. That kind of scenario is very common. Groundwater and surface divides coincident in section A. In the B, as we have discussed, the groundwater divides located outside the basin due to synclinal structure, as you can see here because of geological setup. C is the inflow from outside the basin due to fault. So from other basin, adjacent basin, water is coming inside this basin. Likewise, we can analyze things. If it is a metamorphic setup, metamorphic geology or rocks are there, then catchments of groundwater basin provides useful indices of recharge, because we are not only looking for water, presence of water, occurrence and yield, but also looking how it will get, our aquifers will get recharged, because today we may get the water in these aquifers, but if there is no recharge possibility, then it is a real challenge. So in some regions the geological setup or strata may have been folded into domes, troughs, anticlines, synclines, and introducing much uncertainty in forecasting of aquifer distribution. As here you are seeing in different, that the first one here we are having anticline, in this one we are having a syncline scenario, the top part has got eroded. So only in the section you can understand, or on the surface if you measure the attitude of beds, you can understand which is syncline, which is anticline. And a monoclinal situation is also there, that rocks are simply all layers are having same inclination throughout, and there might be a scenario of plunging anticline, plunging synclines, or a doubly plunging and so on. So if this kind of information is made available in the early stages of groundwater exploration through geological methods, then this becomes much easier to find out a good amount of water and with minimum efforts. These structures also play, though it is not a part of this course, but let me tell you, these structures are equally and more important in case of finding oil and gas, because there are trap rocks and other rocks are important in those situations where the gas will get stored and where the oil will get stored, natural oil. There these structures play a very important role, including in groundwater engineering also. So information, overall information about the depth of aquifer, that means depth of your formations, water bearing formations, topographic slopes, distribution of pressure heads of confined aquifers, that is hydraulic gradient, can be used to delineate even artesian basins and flowing wells areas. Like here, as you can see that this is a unconfined aquifer conditions, and because of piezometric surface which is much above of this ground surface, and therefore the water is almost available at the surface, or water may come out, or you may have a scenario of flowing well. So, these are the without any energy resources one can get water on the surface, but these are not very common thing. I gave example of the Bhabbar zone, which is just south of our Shivalik rocks, all along this foothills of Shivaliks or Himalaya, and there is a Bhabbar zone where you can see many times seepage, water is oozing out from surface, or if there are some open wells and other things, you can also see these artesian wells, especially in monsoon time. Because in unconfined aquifer conditions, these are very much possible, including in confined aquifer also. If these are that's kind of situation, that if water table or piezometric, the pressure air atmospheric pressure level is the piezometric surface is higher than above the ground, then you may get water at that level. So, depending on other aspects, like here flowing wells or artesian wells are more likely to be made in the synclines, or rocks which are folded in synclines, or syncline folds are you are getting, rather than in anticlines, where in synclines rocks comes inside folding towards the core, and in antiform or anticline they go away from the core. So, it is more likely you will get syncline. So, if you are having information about the attitude of beds all for a larger area, and if it is a synclinal folding or syncline folds, then core of the fold, and there are chances that you may get artesian conditions. So, one should, if one should working in the field like this, then one should immediately go in the core to find out water at less depth, or even artesian conditions, or maybe seepage coming out of these rocks. Further, if you look from the top, these informations can also be gathered, like effect of impermeable and impermeable layers on stream flow conditions and springs. So, here there is a sequence of pervious and impervious layers are there, and rocks are dipping towards north in this map by 60 degree. So, you can predict that where it is possible to have springs, like here, like here, like here, here and here, because you are having these are impervious layers, you are having more pervious layers, and so on. So, different kind of setups will help us to find out the springs, stream channels and other things. So, by this you can get lot of information even about the subsurface conditions and availability of water as well. Again, this figure has come. One important statement I would like to make, we know that it has been a famous saying that a picture tells 1,000 words, but let me add one more phrase in it, that a satellite image tells 10,000 words. So, that is why this image is coming again and again, that as you more analyze this image, more interpretation and inferences are made, you get much more in-depth information about the area. So, my suggestions, those who are going to do the field based investigations or in future, they must analyze satellite images extensively, interpret them, make out inferences on them, then other investigations should start. So, again in hard, resistant, impermeable members of a series of tilted beds, that is crossed by a stream, here the not really rocks, but quartz reefs are there which are almost vertical. If even they are tilted, then they can be used for impoundment of water and can be used as a dam access. And then you can see in the upstream side that area will get inundated, in downstream sides you can see better groundwater conditions because of groundwater recharge. Though we say hard rocks, but that we have been saying or discussing, that does not mean older rocks are also having a quite thick weathered zone and fracture zone too. And these are good from groundwater point of view. And the most of the groundwater in these areas in hard rock terrain is found in only on the top part, which is unconfined aquifer conditions. But if we are having such impoundment of water on the surface, then the availability of water and yield will be sustainable from these areas. Even we are having unconfined aquifer conditions and in a completely hard rock terrain like this granitoid. So these are the understanding which we require. Accumulation of water may be indicated by shallow springs and pteridophytes. There are some plants which go deep root system that draws a water supply from near the water table. So these if some field investigation are being done, if people find these kind of plants which are pteridophytes and which are drawing water deep from the aquifer or deep from the water table, which are located in deep water table, that is an indication that water is available there. So growth of vegetation in any part of the earth is indication that some moisture, some water is available, and that will give us indirect evidence of presence of water. This is what we have also discussed when we discuss indirect evidences which we see on satellite images. So growth of vegetation is indirect evidence of presence of water. It is again further proved through these pteridophyte plants. A series of alternating dry and wet stretches along a stream may also indicate the changes in the permeability of rocks along with stream profile. And this is what a figure I showed earlier, this one, that here we are having series of alternate rocks, less pervious, more pervious and so on, and therefore you are seeing these springs and streams. So this part is getting dry again because this is having water rich, so there is a spring. So the water which is coming in this spring is mostly coming from this horizon. Similarly here, similarly here. So from surface we can understand if the arrangement of rocks are like this, then we know where to get the water. So rather than trying to get water here, which is highly unlikely that you will get, but if I go for searching for water here, I may get water much easier, because I know that by these locations of springs and wet and dry stretches of streams will definitely help me to find out the location of water. So in remote sensing images, as we have been discussing, are useful to distinguish such wet and dry features of streams. Combined studies on geomorphic expressions, that means whatever the present features on rocks which are or features which are present on the surface, attitude of beds are very useful, as we have seen in our discussion also. And based on attitude of beds in like in the field of earth sciences, location and attitude of beds can be used to create geological cross sections, and these geological cross sections can give us some insight about the subsurface geology. Again which will be a much help from groundwater point of view. So before even geophysical prospecting or geophysical explorations are done, before any test drilling is done, one should also utilize this technique of creating a geological cross section by employing location of different rock formations there and their attitudes, dipping and strike, and then creating a geological cross section. That will help us to understand subsurface geology. Here in this you are having a three boundary outcrop of quartzite which are apparently distributed, indicate the shallow bedrock. Outcrops should be properly joined, and the strike of the quartzite or interbeds that can be established here. So what we are doing, application of geological and geomorphological criteria in delineating valley fills. Valley fills, alluvial valley fills are very useful from groundwater point of view. So if in an area alluvial valley fills are there are more chances that one will get the water there. in earlier examples we have also seen, let me like show you here, that even in this area where basement is granite on the top, here in this part you are having unweathered basalt, here the basalt has got weathered, and these are the valley fills areas. So, if you are looking water, the preferred location should be the valley fill, and that valley alluvial filled valleys can be easily identified on remote sensing data or on some geological maps or topographic maps as well. Fractures again very important. We have discussed to some extent that the groundwater well siting in fractured rocks have to take into account the complex and generally unpredicted distribution of fracture openings. So, what it means basically, at one location you are getting a fracture, but it is not necessary that in subsurface conditions or even in lateral extent the same fracture will continue for a long time. So, this is it is a complex situation and unpredicted distribution of fractures and associated openings, and how the water will move or get accumulated and circulate. Many times it is very challenging, but in hard rock terrain you do not have choice. You are only looking for water, mainly the weathered part and fractured part. So, the good reliable fracture mapping for an area is very important. Fracture patterns these introduced, they are important from permeability point of view of the movement of groundwater in horizons and also vertically in the rocks also, not only laterally, but vertically they are very useful. So, on the surface definitely these can be mapped to large extent if it is not covered with vegetation or soil, but in subsurface conditions one has to guess without having any geophysical explorations. So, the fracture intensity, how intense the fracture is, the depth of persistence, how long this fracture is going, interconnection. So, geomorphic features like boulders and other features can give you an idea about how deep these fractures are. And then finally, attitudes of controlled variacity of physical characteristics, cooling history, that is when these rocks were formed, and the direction of tectonic forces. In that Bundelkhand granite where we are seeing quartz reefs running from northeast to southwest direction, that one theory suggests or one hypothesis suggests that there were some major tectonic activities occurred which opened these fractures, and later on the filling hydrothermal fluid has flowed and that has created these quartz reefs. So, if we assume that hypothesis is correct, then we know that what were the directions of tectonic forces, and they will, all this understanding will help us to locate a much better groundwater. Joints are widest near the surface and tend to taper with depth, and this can also happen with fractures also. So, these things have to be kept in mind. Isolated joints may not sustain long term productivity aquifers. So, here what the joints are in the center in this pyramid diagram, where the faults on the one end, cleavage which are the zone of weaknesses on other, and the small irregular fractures are on the. So, all these four things are here: cleavage at the level of minerals, and joints and these fractures at the level of these minor joints are there, small irregularity fractures are there, fracture cleavage is there that can become a larger, so that can become a joint plane, shear zones are there, so that can become your fault, and then other zones fault breccias also there, and myelonite and other things which is less concerned from groundwater point of view. So, relation between cleavage, fracture and joints and faults is shown from this. So, isolated joints, if you find an area on surface that joint sets may not have very good from groundwater point of view. So, further the rocks subjected to folding may develop several intersecting sets of joints, and which may be compressional or tensile. So, because of these tectonic activities or compressional forces which may develop folding and other things, subsequently joints, parallel to fold axis and so on. But this is more if you are having a small area and all kinds of investigations are possible, then this can also be done. So, as we have seen that joints, a joint is a set of family of parallel evenly spaced joints that can be identified through mapping and analysis of their orientation, spacing and physical properties. A joint system consists of 2 or more intersecting joints. There may be even 3 sets of joints also. So, if there is more jointed rocks are there, good from groundwater point of view. Identification of types of joints is very useful for siting a well. As here you can see that very clearly you can see one set of joints which are running parallel, another set of joints like this, and there is third set of joint like this. So, again these joints are if you find a exposure of rocks such like this on surface, then where the density of joints is more like in this part, then these are good from groundwater point of view. So, presence of major sets of joints may usually be inferred from marked trellis pattern of streams. So, surface drainage streams will also develop along with, because these are where the water can, these are lower part and where the water can flow easily. So, even if you do not see any surface, but you see the growth of vegetation, you see the drainage network has been developed along. So, this trellis pattern of a stream network indicates that the rocks are jointed, and they will this trellis pattern will also tell you that how what are the orientations of these joint planes are there. Now, there are probability of intersecting fractures in a well decreases as the dip increases, and this kind of a diagram which is from very famous book of by Karanth. Earlier in this course I have mentioned that whenever you are looking for some literature on groundwater or groundwater engineering, try to read Indian books. Indian books I mean written by Indian authors, because these books cover mainly the Indian types of geologic and hydrologic or groundwater conditions. So, if we read the books which have been written, maybe written nicely by international authors, their examples are from different countries. So, we cannot, we do not develop a good understanding about the groundwater conditions of our India or our country. So, it is always, in my opinion, it is always, I always preferred in groundwater engineering that we should all try first to follow the Indian authored book rather than foreign authored books. So, this all this will help to understand our site specific conditions about the depth and direction, fracture, joints, and of course, our aim is to find out water wearing horizons. That is our main aim in this discussion also. If there are relatively few large and definite joints are there, then it may be possible to ascertain approximate direction and angle of their dip and locate the well far enough down depth of joints to intersect it sufficiently below the water table. That means more structural analysis is required, and all these things are done, more intense such analysis is done where we are having more scarcity of water or aquifers are very deep. Then we try to exploit as much as information is available on the surface, and that information or that data is collected in the field. Then we will do all these kind of analysis to approximate a certain approximate direction and angle of dip to locate well for far enough down dip to joint where these are intersecting. In that way it will give us a more reliable water resource, groundwater resource. So, these aspects basically will dictate the type and depth of wells in hard rocks. So, the study of fractures, study of weathered zone, study of joints are very important from groundwater point of view. So, this is bringing the end of this discussion. In the next groundwater exploration, we will discuss something more related with this groundwater exploration. So, thank you very much.